Hello everyone, welcome to this lecture series on linear algebra. This is the third lecture of the series, and today we are going to talk about the inverse of a matrix, and in particular we are going to talk about two methods, the normal form of a matrix and Gauss Jordan method. Okay, so I'm assuming that you already know what is the inverse of a matrix. If you are given a square matrix, how to calculate inverse using minors and cofactors. So we are not going to discuss that, but we'll talk about uh, using the elementary matrices and using the elementary transformations to find the normal form, and then using normal form to find inverse of matrix, and also the Gauss Jordan method to find the inverse of a matrix if it exists. Okay, so first we'll take this definition on what are elementary matrices. In the last video we talked about elementary transformation, and so these two are not to be mixed. Okay, elementary transformations are three transformations where we can interchange rows. We can multiply a row with a non-zero constant, or we can add one row to a constant time another row. Okay, but elementary matrices uh, are obtained by using those elementary transformations only. Okay, so an elementary matrix is one that is obtained by performing a single elementary row or column transformation on an identity matrix. Okay, so elementary transformation, as I said, there are three elementary transformation: interchange of rows, multiplying with a non-zero constant to any row, or adding one row to constant time and another row. And similarly these three operations can also be done on column. So if we take the identity matrix and apply any one single transformation on this identity matrix, then an equivalent matrix will be obtained, and that equivalent matrix will be called the elementary matrix. Okay, so elementary matrix is obtained from the identity matrix by performing a single elementary operation, either a single elementary row operation or a single elementary column operation. Okay, uh, say for example, if I take a 3 by 3 identity matrix and use this elementary row operation, which is interchange of row 1 and row 3, then it will give me another matrix where first row becomes the third row and third row becomes the first row. Then this new matrix, which say I denote with R13, is a elementary matrix, because this matrix is obtained from the identity matrix by performing a single elementary transformation. Okay, and in this case a single row transformation is used. Okay, similarly, say I take another example, that again I start with the identity matrix. Okay, and we say apply 2 times row 2 and impact is on row 2. Okay, so that means second row is multiplied with a non-zero constant 2. Okay, so the new matrix, see, second row is multiplied by 2, so this element 1 becomes 2. So this matrix, which is denoted by A2, is again a elementary matrix, because it is obtained from identity matrix by applying a single elementary row operation. Okay, so from here if we reach to R13 this, and again I apply another transformation on this, then the new matrix will not be elementary matrix, because it will be obtained by two-step procedure from here. Okay, so just one elementary operation on the identity, that whatever matrix you will get, you will call it elementary matrix. Say one last example, say again a 3 by 3 identity matrix, if I start with and apply that row 1 plus 2 times row 2 and impact is on row 1. Okay, so that means row 1 is changed, and how it is changed, that the first row plus 2 times second row. Okay, so clearly this element will be 2 plus 2 times this, so here we will get a 2. Okay, so 1 2 0 first row, second and third row are unchanged, there is no impact on second third row. So this matrix again, it's a elementary matrix, because it is obtained from identity matrix by a single row transformation operation. Okay, now this elementary matrix, it will benefit us in this sense, that the elementary row or column transformations of a matrix A can be obtained by pre or post multiplication with the corresponding elementary matrix. Okay, so what we mean to say here is that if you are given a matrix A and if I apply any elementary row transformation on this matrix A, that can be obtained by the pre-multiplication of the corresponding elementary matrix. Okay, so if I have a uh, say if I have a matrix of 3 by 3, and if I interchange the first row and second row of the matrix A, okay, so if correspondingly I take the 3 by 3 identity matrix and change the first and second row, so that will be the corresponding elementary matrix, and if I pre-multiply this matrix A with the corresponding elementary matrix, the same operation which I apply directly on A can be obtained. Okay, so let me give one example on this to make sure that you get it. That let A be this 3 by 3 matrix, and the transformation that we use is say row 1 interchange row 2. Okay, so these elements A21, A22, A23, they will go to the first row. Okay, and the elements of first row, they will move to the second row. Okay, so interchange of row 1 with row 2, we obtained this transformed equivalent matrix from the matrix A. Now this method says that if you apply elementary row transformation on matrix A, okay, so that you from A matrix you obtain this new matrix. This can be done by pre-multiplication with the corresponding elementary matrix. So by using the same transformation, if I calculate first the corresponding elementary matrix, so here the size is 3 by 3. So if I transform the 3 by 3 identity matrix by row 1 interchange row 2, then this matrix will be the corresponding elementary matrix of identity. Okay, so row 1 and row 2 are interchanged in the identity matrix. Okay, so the same transformation is applied on the identity matrix. Now this says that whatever transformation you apply on A, so the result can be obtained by pre-multiplication of the corresponding elementary matrix. That means if I multiply this matrix R12 to A, in fact pre-multiply, so if I calculate R12 times A, it will give me the same matrix which I have calculated by the interchange of these matrix A. Okay, so if I calculate R12 times A, that means this matrix multiplied with the original A matrix, then the result will be that the row 1 and row 2 of the matrix A will be interchanged. Okay, so I will get this matrix. Okay, so this is very much clear that the row transformation on a matrix A can be obtained by pre-multiplication. Okay, there is a pre-multiplication with the corresponding elementary matrix. Similarly, if instead of row operation we apply any column operation, okay, on the matrix A, so the result can be obtained as a post multiplication with the corresponding elementary matrix. Okay, so let me take an example again. Say again you are given a matrix A and we use the column transformation, that third column is added to 2 times first column and the result impacted on the third column. Okay, so column 3 is rewritten as column 3 plus 2 times column 1. So this column is added to 2 times first column. Okay, so A13 plus 2 times A11, that becomes the first element of third column. Okay, so similarly the second element and third element of the third column is changed by this transformation. Now this result says that this same transformation, if we apply on 3 by 3 identity matrix to find a elementary matrix, then this result can be obtained as a post multiplication. Okay, so if I use this transformation and calculate the corresponding elementary matrix, so clearly if I use 3 by 3 identity matrix and use column 3 plus 2 times C1, so this element will become 2 because this was 0 plus 2 times 1. Okay, so this becomes 2 and other element remains same. Okay, so this is the elementary matrix obtained from the identity matrix by this transformation C3 plus 2 C1 impact on C3. Okay, and so this method says that if I calculate A times E13, okay, so if this E13 matrix is post multiplied to A, I should get this same matrix as this. Okay, so A times E13, if I calculate product of these two, it will give me this matrix which is same as the transformation of the matrix A by using the same transformation, that column 3 plus 2 times column 1 and impact on column 3. Okay, so that means any elementary row transformation or column transformation can be obtained by pre-multiplying or post-multiplying by the corresponding elementary matrix. Okay, so here clearly the column transformation on A can be obtained by post multiplication with corresponding elementary matrix. That means if we are doing any row operation, then its impact is on pre-multiplication. Okay, and if we are doing any column operation, its impact is a post multiplication by the elementary matrix. Okay, so if you remember this, then it will be easier for the calculation of the normal form of matrix. Okay, so now let us take this definition on what we mean by the normal form of a matrix. So every non-zero matrix A of rank R can be reduced by a sequence of elementary transformations to one of the forms. Okay, these four forms called the normal forms of A. Okay, so if you are given any matrix A, say whose rank is R, then by if you apply sequence of elementary transformations, and in this case you can apply row transformation as well as column transformations, or a combination of row and column transformations, and the matrix A will reduce to one of these forms, where the first form is the that it will reduce to the complete identity matrix, or it will be reduced to a identity matrix of rank R, and below this there is a matrix of zeros. Okay, or a identity matrix of rank R with some columns of zeros. Okay, here some rows of zeros are there, so here some columns of zeros are there, and or a identity matrix of rank R with some columns zeros and some rows zeros. So this complete matrix consists of a portion of R size identity matrix and some zeros, where these zeros are actually zero matrices of different sizes depending upon the size of original matrix. Okay, and so any one of the forms if you obtained, the form is called the normal form of A. And further, corresponding to every matrix A of rank R, so whatever matrix you reduce to one of these form, there exist non-singular matrices P and Q such that PAQ is normal form. Okay, so that means A is reduced to one of these forms, and then it will be equal to P times A times Q, where P and Q are non-singular matrices. Okay, so they are definitely square matrices whose determinant is non-zero. Okay, and if the normal form is completely identity matrix, okay, this first case, then the matrix A will be invertible. Okay, so if PAQ is identity, then A is invertible, and you can calculate A inverse as product of Q times P, where Q is the post matrix and P is the pre matrix of A. Okay, and in any other case the matrix will not be invertible, because you can see there is a zero row or zero column present. So in a matrix is not invertible, because determinant, it may not be square matrix, or if it is square, then the determinant is zero. Okay, so non-invertible matrix. But in either case, P and Q will be non-singular. Okay, but you can calculate inverse only when this PAQ will be equal to the normal form, where normal form is the complete identity matrix. Okay, then it is invertible, otherwise it is not invertible. So to find the normal form, basically there is a procedure, and you have to follow this procedure, or you can say this algorithm, to find the normal form. And so if you are given a matrix A which is say of m cross n order, then now we start with writing this matrix A as I times A times I, and clearly A times I is A and I times A is also A, so they are equal. But The pre-matrix identity is depends on how many rows are there, and post-matrix identity is depending upon how many columns are there. Okay, so these identity matrix may not be of same size. For a square matrix they are of same size, otherwise the pre-matrix is m cross m identity matrix. That means depending upon how many rows are there in matrix A, and the post identity matrix is a n cross n identity matrix depending upon how many columns are there in the matrix A. Okay, so the idea is that we apply elementary transformations, the row operations or column operations, and reduce the left hand side of the matrix, this equation, this matrix A on the left hand side, to one of these forms. And whenever we apply the row operations on this matrix, the row operation will impact the pre-multiplied matrix. Okay, so that will, the same row operations will be applied on the identity matrix which is pre-multiplied to A. And whenever we will apply a column operation on this equation or on this matrix left hand side, the same will have impact on the post multiplied matrix. Okay, so row operations are impacting the pre-multiplied matrix, and column operations will have impact on post multiplied matrix. Okay, so apply row and column operations to reduce the matrix on the left of equation to normal form. Okay, that means one of these forms. Okay, and for each row operation on the left, apply the same row operation on the pre-matrix on the right, and for every column operation on the left, apply the column operation on the post matrix on the right. Okay, so whenever we apply row operation here, we apply the same row operation on pre-matrix. Whenever we apply column operation here, we apply the same column operation on post matrix. Okay, so now let us take, say, one example. We start with a simple example of 3 by 3 matrix, and we have to reduce it to a normal form. Okay, so what we start with is a by writing that A is equal to identity times A times identity, and in this case, because it's a 3 by 3 matrix, 3 rows and 3 columns, so both identity matrix are of same size, 3 by 3, and the second one is also 3 by 3. Okay, so we can now rewrite this by writing left hand side as this matrix, and also writing identity matrix is of order 3. Okay, so this left hand side A matrix, this side I, A, I, and this A we are not writing this matrix because we are not going to apply any transformation on this matrix on the right hand side, so it will go on like writing as A. Okay, so whenever we will apply any row operation on the left hand side matrix, the same row operation will be on this pre-multiplied matrix, and whenever we apply a column operation on the left side, that column operation we will apply on the right hand side on the post multiplied matrix. Okay, so we have to reduce it to like try and reduce it to identity matrix. So we have our first position at 1 position 1, so we'll use it to make the bottom two element 0. 1 is already 0, so we just need to make this one as 0. So we'll apply row 2 minus row 1 on impact on row 2 to make this 0. Okay, so if we apply row 2 minus row 1 impact on row 2, this will reduce this element to 0. Okay, 1 minus 1, and so 2 minus 1 is 1 and 3 minus 2 is 1. Okay, so impact is on second row only, you know, first row and third row remains same. And whenever we apply row operation, the same row operation is to be applied on pre-matrix, not on the post matrix. Okay, so post matrix remains same. The pre-matrix we apply same row operation, row 2 minus row 1, and impact on row 2. Okay, so row 2 changes as row 2 minus row 1, so 0 minus 1 becomes minus 1, 1 minus 0 1, and 0 minus 0 0. First row and third row remains same. Okay, uh, now again we have a 1 here. Okay, so we can use it to reduce this. Okay, minus 1 to 0, so we apply row 3 plus row 2 impact on row 3. Okay, so immediately you can see that third row when added to second row, the third row vanishes. Okay, and the elements become 0. Thus again a row operation, so say same has to be done on pre-matrix. So third row added to second row element wise, so 0 plus 1 plus minus 1, so minus 1, 0 plus 1 1, 1 plus 0 1. Okay, so third row, first and second row do not change, and post matrix no transformation is applied, only row transformation is there, so no change in post matrix. Okay, okay, so now In the third row it is already everything is 0, so now we can apply, say, column transformation, use this element at 1 1 position and make these two elements at 1 2 and 1 3 position to make them 0. So we can apply C2 minus C1 on impact on C2, and we can apply C3 minus 2 times C1 impact on C3 to make the non-diagonal elements of row 1 exactly 0. Okay, and I'm saying column operation, so pre-matrix will not change and all column operation will impact the post matrix. Okay, so let us apply these two C2 minus C1 impact on C2 and C3 minus 2 C1 impact on C3. So these two elements become 0 by that operation, and because these two elements were 0, so rest of the element do not change. Okay, and the same operation we apply on the post matrix. So it was identity earlier, so it was C2 minus C1, so 0 minus 1 becomes here minus 1, and C3 minus 2 times, so it becomes minus 2. Rest of the element remains same because there is 0 0 here. Okay, now we can use this second column and make this element 0. Okay, so that diagonal element becomes 1 and non-diagonal becomes 0, and in the process sum of the diagonal also becomes 0. So we have identity matrix constructing here. Okay, so C3 minus C2 should be the next operation. Okay, so C3 minus C2 impact on C3, it will make this element 0, and because the column operation, so it will impact the post matrix. So same C3 minus C2, so this column minus second column impact on third column. Okay, so first and second column will not change, pre-matrix will not change. Okay, so minus 2 minus minus 1, so minus 2 plus 1 is minus 1, 0 minus 1 is minus 1, and 1 minus 0 is 1. Okay, so clearly you can see we have obtained one of the normal forms. Here we have a I2 2 by 2 identity matrix with a 0 matrix which is of the 2 by 1, and a 1 by 2 0 matrix, and a 0 by 1 by 1 0 matrix. Okay, and this matrix which is pre-multiplied we call it P, and this matrix post multiplied we call it Q. So we have a normal form equal to PAQ. Okay, so we can write this left hand side as I2 0 0 0, where these zeros are 0 matrices of different sizes, and right hand side becomes PAQ, where P is the pre-matrix, Q is the post matrix. Okay, and clearly you can see P and Q are non-singular matrices, and because we are starting with identity matrix and applying operations, so uh, identity matrix is non-singular, so definitely we are always going to get P and Q as non-singular matrices. And on the left hand side, clearly I2 means this 2 by 2 identity matrix. This 0 matrix is a 2 by 1 0 matrix. This 0 matrix in the bottom is 1 row 2 columns, so 1 by 2 0 matrix, and this fourth 0 matrix is a 1 by 1 0 matrix. Okay, so we just bifurcate like this. Okay, so I2 0 0 0, and from here you can see that because we get I2, so this A rank of matrix A is 2. Okay, so we started with the matrix A which is a 3 by 3 and rank is 2, so clearly the matrix A is not invertible here. Okay, so P and Q are non-singular, but A is non-invertible matrix and rank of A is 2. Okay, so let us take another example. Say find the non-singular matrices P and Q such that PAQ is the normal form of matrix, where A is a non-square matrix. So we have 3 rows and 4 columns, so 3 by 4 matrix. Clearly inverse is not in picture here, but we are trying to find out the normal form and the non-singular matrices P and Q. So we have to again start with A is equal to IAI, but in this case both the identity matrices are of different sizes. The pre-matrix depends on number of rows and post matrix depends on number of columns. So pre-matrix will be a 3 by 3 identity and post matrix will be a 4 by 4 identity. Okay, so we start with writing A is a 3 by 4 matrix, so we have to write IAI, but the first identity matrix is 3 by 3 and second identity matrix is 4 by 4. Okay, so now we can write this A matrix on the left hand side and right hand side 3 by 3 identity matrix times A times 4 by 4 identity matrix. Okay, and then you can start using operations, try to reduce it to normal form. and you can start with a row operation or a column operation. You can use some row operations then column operations, or you can mix, use one row operation then column then row then column. Okay, so whatever operations you want you can apply so that it reduces to normal form. The only thing is, whenever you apply row operation here, apply the same row operation on pre-matrix, and whenever you apply a column operation on left hand side, apply that column operation on the post matrix. Okay, so this first element is 1, so we'll use this element to make the bottom two elements 0. So we will apply row operations, row 2 minus 2 row 1, impact on row 2, so this element will become 0, and row 3 minus 3 row 1. Okay, so 3 minus 3, so this element will become 0. Okay, so, and because they are row operations, the same are to be applied on pre-matrix. Okay, so 2 minus 2 0, minus 2 minus 2 2 times 2, so minus 2 minus 4 is minus 6, 1 minus 6 minus 5, and 3 plus 4 will be 7. Okay, now 3 this row minus 3 times this row. Okay, so 3 minus 3 is 0, 0 minus 3 times 6, so minus 6, 4 minus 9 minus 5, and 1 plus 6 is 7. Okay, the same row operations here, so second row minus 2 times first. Okay, so 0 minus 2, so this becomes minus 2, rest becomes 1 0, and third row minus 3 times first row, so this element becomes minus 3 0 1. Okay, now you can clearly see second and third row are same, so you can apply row 3 minus row 2 and remove third row as 0 0 0. The same operation to be applied here. Okay, so row 3 minus row 2 on row 3, so all elements in third row become 0, and here row 3 minus row 2 impact here, so we are at minus 1, 0 minus 1 is minus 1, and 1 minus 0 is 1. Okay, no operation on post matrix because row operations are applied. Now we can use this one and make these element in the first row non-diagonal elements as 0. Okay, so c2 minus 2 times c1, c3 minus 3 times c1, and c4 plus 2 times c1. Okay, to make this elements 0, or you can choose your own operations and try to reduce it to normal form. Okay, so we apply these column operations so that these three elements become 0. Okay, because now we are applying column operations, so the impact will be on the post matrix. Okay, so c2 minus 2 times c1 gives this element minus 2. Similarly, this becomes minus 3 because third column minus 3 times first in identity, and c4 plus 2 times c1 makes this element 2. Okay, now we can use this element here to make these two elements 0. So c3 is impacted by c2 to convert this to 0, and c4 using c2 to convert this to 0. Okay, so we apply uh, okay, here we have done in a different way, but the same can be done also. Okay, so here it is done that the all the elements of the second, third and fourth column which are non-zero are made 1. Okay, so we used minus 1 by 6 on c2, impact on c2. Okay, so this element will become 1, minus 1 by 5 on third column, and so this element will become 1, and 1 by 7 on c4, so this element will become 1. Okay, and so because these are column operations, so same column operations here. Okay, so second column is changed as minus 1 by 6 on second column, so minus 1 by 6 of these two. Okay, minus 1 by 5 of third column, so minus 1 by 5 on these two elements, and 1 by 7 on fourth column, so 1 by 7 on the fourth column. Okay, and now again uh, ultimately we have to use that we have to make these two elements 0, so c3 minus c2 and c4 minus c2. Okay, so c3 minus c2 on c3 and c4 minus c2 on c4. Okay, so this could have been done directly from here. Okay, but okay, two steps. So again column operations, so we have to apply the same column operations here. So third column minus second column, so this third column will change, and fourth column minus second column, impact on fourth column, so fourth column will change. Okay, nothing changes in pre-matrix in these two cases because no row operation is applied. Okay, so now we have a normal form on the left hand side. You can see a 2 by 2 identity matrix. There is a 0 matrix, there is a 0 matrix in bottom and 0 matrix here. Okay, this becomes a p matrix, this becomes the q matrix. Clearly the two are non-singular. Okay, So we have normal form I2000, which is equal to PAQ, where P is a 3 by 3 non-singular matrix and Q is a non-singular 4 by 4 matrix. Okay, and here I2 means this 2 by 2 identity. This 0 matrix is a 2 by 2 0 matrix. Okay, this 0 matrix at the bottom is a 1 cross 2 0 matrix, and this 0 matrix is a 1 cross 2 0 matrix. Okay, so I have used these operations. You may do a different set of operations, and because these matrices are impacting by these operations, this clearly means that these matrices P and Q, they are not unique. Okay, you may end up with different P and Q matrix depending upon what operations you apply. Okay, but nevertheless, if we are going to find inverse in some case, then inverse has to be unique. Okay, so maybe there is another example, and in this case you can see that the rank of matrix is 2 because we have obtained the identity matrix of size 2. Okay, so say find the inverse of the matrix by reducing it to normal form. Okay, so now we have to find inverse by reducing to normal form. Matrix is a 3 by 3, so we again start with A is equal to I, where both identity matrices are now same size because rows are 3, columns are 3. Okay, so just put the left hand side as this matrix and write the identity matrices. We write the middle as A because we are not going to change it throughout the process. So now apply some row and column operations and transform this to identity. If the matrix has inverse, that means the left hand side is going to be I3, complete identity matrix. Okay, so whatever row operations you use it on pre-matrix. Whatever column operations you use on post-matrix. Okay, so here we are using row 1 minus row 2 on row 1. Okay, so we are changing first row by row 1 minus row 2. Okay, this will help as the first element will become 1 and the other two will become 0. Okay, so first row changes impacted by row 1 minus row 2. Okay, second and third row do not change, and whatever row operation is applied here, the same on pre-matrix. So first row is changed as row 1 minus row 2. Okay, now clearly we can use this first element and make this element 0. Okay, so row 2 minus 2 times row 1. Okay, so row 2 minus 2 times row 1 impact on row 2, so this element goes to 0. The same on right hand side pre-matrix, row 2 minus 2 times row 1, so 0 minus 2, so it becomes minus 2. 1 plus 2 becomes 3, and 0 with 0 remains 0. Okay, no change in post matrix. Okay, so now we have here 1, these two are already 0, these two are already 0. We have to make this as 1, this as 1, and this non-diagonal as 0. Okay, so we can use like C2 plus C3 impact on C2, so minus 3 plus 4 makes it 1. Okay, so I hopefully we have done this. Okay, C2 plus C3 impact on C2, yeah, so it makes this element 1, and this goes to 0. And so the column operation, so post matrix is affected. Okay, so C2 plus C3. Okay, so 0 plus 1 becomes 1 here. Okay, now we only need to do is make this element 0. So either you can use row 2 minus 4 times row 3, or you can use C3 minus 4 times C2. Okay, so here we have used row 2 minus 4 times row 3 impact on row 2. Okay, you could have also used C2 minus 4 times C3 minus 4 times C2 impact on C3, and that would have also produced the same identity matrix, but we are using row operation, so impact on pre-matrix. If you use column operation here, impact on post matrix. Okay, okay, so second row minus 4 times third row. Okay, so second row minus 4 times this, so this becomes minus 4. Okay, so clearly left hand side is I3, and so we have this as P and this as Q matrix. So I3 equals P A Q. P is this matrix, Q is this matrix, and because we have obtained the full identity matrix, that means a rank of A is 3. So A is invertible, and A inverse we can calculate as Q times P. Okay, so this is the Q and this is the P, so we can just multiply these two and we can calculate the A inverse matrix. Okay, so if you multiply these two, we'll end up with this matrix. Okay, so which is the A inverse of the original matrix. So this is your normal form of matrix, and we can find inverse if the matrix is invertible. And you will always remember that A inverse, which is product of QP, if A inverse exists, this is unique. But these two matrices P and Q, they are not unique. They depend upon what operations are being used. Okay. Now we come to our second definition, which is Gauss Jordan method for finding inverse. Okay. So what we do in normal form to find inverse is we apply row operations and column operations and their combination, and the impact is on pre-matrix or post-matrix. But instead of applying both row and column, if we apply only row operations or only column operations, the impact will be either on the pre-matrix or only on the post-matrix. Okay, so instead of PAQ, if we apply only on row operations to convert identity, so P will convert into A inverse, because PAQ is actually PAI equals I. Okay, so PA equals I means the P has to be Q inverse. Okay, so that is the idea of Gauss Jordan method, that if you have an n cross n matrix, that if you have a square matrix which is invertible, so that will be done if and only if A is row equivalent to identity. And in this case, any sequence of elementary row operations which reduce A to identity also transform identity to A inverse. Okay, so whatever operations, elementary row operations you apply to reduce A matrix to identity matrix, the same row operation will be done on the pre-matrix, so it will convert identity matrix into A inverse. Okay, so the proof is very simple in this case, that let the successive row transformations which reduces A to identity result from pre-multiplication of elementary matrices. Okay, so that okay, so if we apply row transformations on A, okay, so each row transformation we know it is a pre-multiplication by elementary matrix. Okay, so if we apply successively one after another row operations, so it will be a pre-multiplication of all the elementary matrices. Okay, so that we can write that the A matrix we apply one elementary operation, then on the new matrix we apply another elementary operation, and so on, some p number of operations which convert A matrix to identity matrix. Okay, so if the same set of operations are applied on identity matrix, then it will convert into A inverse. Okay, so the proof is simple, that if A is invertible, then we can post multiply on both sides with A inverse. Okay, so this left hand side and right hand side both are post multiplied with A inverse. Now A times A inverse, if A inverse exists, so this product is identity. Okay, so the left hand side becomes identity uh, pre-multiplied with these elementary matrices equals the inverse. So clearly these two equations says that if a sequence of elementary row transformation or elementary matrices are applied on A to convert this A into identity, the same elementary transformations when applied on identity, it converts it into A inverse. Okay, so the idea of Gauss Jordan is very simple, that instead of applying a combination of row operations and column operations, we apply only row operations. Okay, or you say you can also apply only column operations but no mixture of row and column operations. Okay, so the algorithm for finding inverse now is a bit simpler, in the sense that we do not need to write A is equal to IAI, because we are only going to apply row operations, so we are only going to impact the pre-matrix identity. Okay, so it is sufficient to write the matrix A and I. Okay, so we can write it in the augmented matrix form, in a single matrix, the A matrix, whatever square matrix is given, and the same size identity matrix, the size of A. Okay, so that it is easier to apply the row operations, whatever row operation we apply on A, the same row operation we apply on this identity. Okay, so and as soon as this A converts into identity, this identity matrix converts into A inverse. Okay, so if A is row equivalent to identity, then this augmented matrix, as soon as A is converted into identity, the identity is converted into A inverse. Okay, so we will get the A inverse from there. And in case the A is not converted into identity, then whatever matrix is obtained here is not A inverse. Okay, and in fact then A does not have an inverse. Okay, So we take say one example, say use Gauss Jordan method to find inverse of matrix A. Okay, so given this matrix, so idea is very simple, that we write the augmented matrix A and I. A is the 3 by 3 matrix, this, okay, and the same size identity matrix. Okay, so writing inside a single bracket, it is easier to apply operations. Now whatever operations are applied, it is applied on the whole uh, of the matrix, and we are going to use only row operations now. Okay, so we have to convert this 3 by 3 matrix into identity matrix. Okay, so this element is already 1, we will use it to make these two elements 0. Okay, so row 2 minus row 1 and row 3 plus 2 times row 1. Okay, so row 2 minus row 1 impact on row 2, so 1 minus 1 is 0, 3 minus 1 is 2, minus 3 plus minus 3 minus 3, so minus 6, and we'll apply the same row operation here. So 0 minus 1 minus 1, 1 minus 0, and 0 minus 0. Okay, row 3 plus 2 times row 1 impact on row 3, so third row is changed by row 3 plus 2 times row 1, so minus 2 plus 2, 0, minus 4 plus 2, minus 2, minus 4 plus 6, 3 to the 6. Okay, so 2, 0 plus 2 is 2. Okay, and 0 1. Now you can reduce this third row minus second row to make this element 0. We have to make for the 3 by 3 non-diagonal elements, we have to make 0, but we have to apply only row operations. Or you can divide second row by 2 and make this element 1. Okay, and then remove this. So either way you can do it. Okay, so here we are doing that third row plus second row impact on third row to make this element 0. Okay, so 0 minus 0, 1, minus 2 plus 2, 0, 2 minus 6 minus 4, 2 minus 1, 1, 0 plus 1, 1, and 1 plus 0 is 1. Okay, so now it becomes a upper triangular, the bottom elements gone. So now we can start using this element and make above elements 0. Okay, so we'll apply uh, row operations only. Okay, we will not apply any column operation. So apply row operation, make use this element and make these two elements 0, or you can divide second row with 2 and third row with minus 4 to make these two element 1 first. Okay, so either way you can continue. Okay, so here we are doing that, we are changing the third element to 1 by dividing with minus 1 by 4 on R3, impact on R3. So this element becomes 1 and all the other elements in this row are divided by minus 1 by 4. Now we'll use this one to make these two elements 0. Okay, so row 2 plus 6 times row 3. Okay, so this row plus 6 times this will make this element 0, and row 1 minus 3 row 3 impact on row 1, so this will make 3 minus 3, 0. Okay, so these two elements become 0. The same are to be applied on this side. Okay, the others will not change because other elements of row 3 are 0, so there is no impact on the elements of row 1 and row 2. Okay, so only these two will change, and these will update accordingly. Now we'll use this element, make this 0, or you can divide this second row with 2. Okay, again don't use column operations. Okay, so half of row 2 impact on row 2, so this will become 1 and these will change. Okay, and finally use second row to make this element of first row 0, so row 1 minus row 2 impact on row 1. Okay, so row 1 minus row 2 impact on row 1, it converts this to 0, so it becomes the identity matrix of 3 by 3 here. Okay, the same row operation on there, right? So whatever matrix we get here is the A inverse, because we have obtained a full identity matrix on this side. Okay, so the inverse matrix of A is A inverse equals this matrix. Okay, so the idea is very simple, we only applied row operations, no column operations, no mix of row and column operations. Okay, completely use the row operations, or if you want, completely use the column operations. Okay, use Gauss Jordan method to find the inverse of a 4 by 4 matrix. Okay, so again we are going to use Gauss Jordan method to solve this example, and we are going to use only row operations. Okay, so we are going to write augmented matrix AI, where A is a 4 by 4 matrix, so identity is also a 4 by 4 matrix, same size. Okay, and now we are going to convert this 4 by 4 matrix on the left as identity, and the same operations will convert this identity to A inverse. So use the first element, make these three elements 0. Okay, so row 2 minus row 1 impact on row 2, row 3 minus row 1 impact on row 3, row 4 minus row 1 impact on row 4. Okay, so simple, these three operations, this will convert these elements to 0. And the same operations on this identity, if you see 0 minus 1, so it becomes minus 1. Okay, so these elements become minus 1. Okay, so same row operations. Now we can use this second element and make these two zeros. So that means row 3 minus row 2 impact on row 3, and row 4 minus row 2 impact on row 4. So these two will become 0. Okay, same on this side. Okay, so there will be impact here also. Okay, so row 3 minus row 2 impact on row 3, row 4 minus row 2 impact on row 4. So these two elements become 0, and there are changes in row 2, row 3 and row 4. Okay, row 1 and row 2 do not change, there is no impact. And finally, to make this identity, we have simply used row 4 minus row 3 impact on row 4 to make this element 0. Okay, the same on this side. Okay, so this becomes the identity matrix of size 4, and so whatever matrix we obtain here is the inverse of matrix A. Okay, so we have the A inverse as this matrix. Okay, so this was your procedure to find the inverse by Gauss Jordan method. Okay, so now this is it for today. We'll continue with this, and in the next lecture we'll learn about system of linear equations. Okay, till then, have a very good day.